tell you with sincere excitement that we are going to talk about the next group of reactions, which we'll be talking about for a long time. All right. And these are E2 reactions. All right. So now we've talked about alkyl halides. You know that alkyl halides, when treated with a nucleophile, can undergo substitution reactions, right? Well, nucleophiles, funny enough, right, kind of look like bases, and oftentimes actually nucleophiles can act as bases. So we're going to have to hold these two in tension with each other, because when alkyl halides are treated with a strong base, it can undergo elimination at the beta carbon. So watch how this works. You have, right, alpha. See your alpha carbon, that's alpha with respect to the halogen, right? So well, there's your beta carbon, and of course if this is a carbon, that's also a beta carbon, right? All the carbons that are one away are the beta carbons. Let's keep this simple for now. So let's suppose that there's only one beta carbon, okay? And if there's only one beta carbon, here's your beta hydrogen, right? And watch this. This comes in here. Well, here's the mechanism down here. That comes in and takes that hydrogen. But, and you'll see why in a minute, why we turn this guy around. This base comes in, attacks that hydrogen. These electrons come down into a pi molecular orbital, and these electrons leave with the leaving group. And if it's concerted, it's going to be E2, right? So that means that these are all going to happen at the same time. Now, this looks like we've got three groups of electrons moving, so don't be confused. 2 doesn't stand for the 2 electron groups moving. It stands for the fact that we've got 2 reactants in this reaction, okay? Can you see what we have now? This base comes in, boom, takes that hydrogen. That goes down to a pi bond, which is to a pi molecular orbital, which is there. And the leaving group leaves, right? And so your base then goes off as the conjugate acid. This is the conjugate. How do you spell conjugate? Conjugate acid. This is the conjugate acid of that base, right? And there's your leaving group. Okay, so this is a brief introduction to E2. Let's look a little more at it. Elimination, E2 elimination is concerted. That means it happens all of the electrons move at the same time, and they move in concert, where the base removes the beta proton, which I showed you in the previous slide, causing the loss of the leaving group and the formation of a CC double bond. So concerted elimination is bimolecular, and that means that you've got 2 reactants. That's what that means, E2 reactants, okay? And it follows second order kinetics. So SN2 also follows second order kinetics. We talked about SN2 in the previous conversation. Now we're talking about E2. Now we're going to introduce it, but they both follow this sort of mechanism here, or this rate law. The rate is equal to K, which this is measured experimentally, times the alkyl halide, times the concentration of the alkyl halide, times the concentration of the base. And that's a rate, and it's measured experimentally, right? So you wouldn't know that necessarily, but we do in lab, we do in Chem 2, we'll do a lab where we solve for K by measuring rates of particular reactions and altering the concentrations. All right, so this is a bimolecular elimination reaction happened. That's what the E2 stands for. I'm repeating myself, I know. In what ways is E2 elimination similar to SN2? Well, that's one way, the rate law, right? There's a leaving group. I guess I should let you answer this, right? There's a leaving group in both of them, okay? But there are some differences too, and I encourage you to think about those differences. I'm not going to go through them with you. Okay, now consider a reagent such as hydroxide, which is a strong nucleophile and a strong base, right? I told you a minute ago we're going to hold these guys in tension. So if it's a strong nucleophile and a strong base, the substitution, look at, this is an example of substitution, right? Where this substitution would be where it comes in. Now, if it's tertiary, if it's a tertiary substrate, it's too hindered, can't get in there, right? Can you see how this is too crowded to get in there? And also the transition state is too high of energy, right? The activation energy is too high. So if if it's tertiary, then you can see that the hydroxide is going to be more inclined to take one of those hydrogens off of there somewhere, right? So if this hydroxide now is not acting as a nucleophile, it's acting as a base, it comes, takes a hydrogen, leaves its electrons behind, goes there to make a pi molecular bond, and that leaving group leaves, right? So you can see that for tertiary, substitution is going to be disfavored. Actually, it's going to be impossible, right? Because we're going to say tertiary substrates don't undergo substitution, in which case, if you have a beta hydrogen, then elimination can occur. All right, we're going to tease these out much more over the next several conversations.